This video continues the series introducing the spatial model of politics. The previous video explained spatial politics in one dimension, culminating in the median voter theorem. This video extends that analysis by considering politics in two dimensions. Politics is rarely truly one-dimensional. Policy conflict occurs along at least two dimensions. Rather than only debating the minimum wage, for example, political actors hold preferences over multiple issues like domestic spending, foreign intervention, civil rights, environmental policy, and so on. To better model real-world politics, then, we might imagine a two-dimensional grid rather than a single line. Each axis represents one policy issue: civil rights, reproductive rights, tax policy, or whatever else is on the agenda. Like in the one-dimensional case, we can place legislators at their ideal points on this grid. Let's imagine a legislature with 3 legislators here. Their ideal point represents their most preferred policy on each of the two dimensions. In this case, legislator A prefers a policy of 3 on the horizontal axis and 5 on the vertical axis. Once again, we have a status quo policy, some existing policy that represents the current law on the books. In this case, the status quo policy is at 5 on the horizontal axis and 5 on the vertical axis. Any new policy must be pitted against this status quo. To determine which policies can beat the status quo, we first have to find every policy that every legislator prefers to the status quo. We need to find their preferred two sets. Each legislator's preferred two set will form a circle just barely touching the status quo policy. Any policy within each legislator's preferred two set, within each legislator's circle, they prefer to the status quo because it's closer to their ideal point than the existing status quo. Like in the one-dimensional case, we now need to find the win set, the set of policies that at least a majority of legislators prefer to the status quo policy. The win set is the intersection of a majority of preferred two sets, in this case 2 of 3. The shaded regions represent all policies that a majority of legislators prefers to the status quo policy. We can see how the win set and preferred two sets change as the legislators' ideal points change. As they get farther away, they get bigger. As they move around, the region shifts. As they get closer, they get smaller. Let's put them back to their original positions and try to find an equilibrium policy, a policy that has no win set. In the one-dimensional case, we know from the median voter theorem that the unique equilibrium is exactly at the median's ideal point. What about in 2 dimensions? We can try to find an equilibrium by selecting a new policy in the win set, making that the status quo, finding the new win sets, and continuing this process until we find a point that has no win set. We'll keep track of the path of these policies with this white line as we go. As we move around, you'll notice that sometimes the win sets get bigger, sometimes they get smaller, but we don't seem to be finding one with an empty win set. In the one-dimensional case, each new policy in the win set shrunk the win set until we got to a place where there was no win set at all. And this next move actually brings us back to the original status quo. Somehow we created a path of policies that took us right back to the status quo. This is called a cycle. We can keep repeating this path over and over again, really infinite many repeating paths, and we'll never find an equilibrium policy. This is potentially concerning because it implies that we can't have a stable outcome. Majorities will always want to change the status quo, and we can't predict what policy will eventually result. But it gets more concerning. It turns out that any policy is reachable in 2 dimensions, no matter how extreme. To show that, I'll move the status quo into the win set over and over and over again, and eventually get to a point that's so far away from both the original status quo and from the ideal points of any individual legislator that we can hardly say the policy improved in any democratic sense. Remember that each of these points I'm drawing is a point that a majority of legislators actually prefers to the existing status quo. So the democratic process of using pure majority rule is actually resulting in outcomes that don't really reflect the common good of these legislators. We've now gone fully off the grid. The original status quo policy of 5 on the horizontal axis and 5 on the vertical axis seems like a much better option than these points I'm drawing now. And in fact, because these policies will cycle, the original status quo is actually in the win set of this new extreme one. This phenomenon, that any policy is reachable no matter how far from the legislator's ideal points, is known as the McKelvey-Schofield chaos theorem. So, unlike in the one-dimensional case, there's no equilibrium policy. There's no median voter theorem. And policy can actually diverge from all legislators' ideal points until it is extremely distant from them. There is, however, a set of very specific conditions where there is an equilibrium policy, but the probability of that set of conditions occurring is essentially zero. The first is when the ideal points of the legislators lie exactly on one line. In this case, it pretty much looks like the one-dimensional case, but the line can be rotated in any arbitrary direction. In this case, the equilibrium policy is just the median legislator's ideal point on that line. The second is when the ideal points are radially symmetrical, meaning we can rotate the ideal points around some central point and still get the same shape. Imagine the spokes of a bicycle wheel, for example, or a starfish. To see why, let's draw in 5 legislators with these ideal points and a status quo policy. The win set will be the overlap of 3 of these preferred 2 sets, because 3 is a majority of 5. Now let's repeat the exercise we did with the first example of moving the status quo around the win set trying to find an equilibrium policy. In this case, we actually do find an equilibrium policy. It's the central legislator's ideal point, something like a multidimensional median voter theorem. Ultimately, though, there's almost never an equilibrium in multiple dimensions, unlike in one dimension. We need these extremely improbable conditions of radial symmetry. Despite this, democracies and other bodies using majority rule seem to be able to enact policies that are stable and don't change all the time. Why is that? The next video will describe how political actors create structures, or institutions, that induce equilibrium policies, even absent these radially symmetrical ideal points.